So I've alluded to the fact that the number of vectors in a set can be related in certain ways to whether the set is linearly independent or linearly dependent, depending on the situation. Sometimes it can't, right? And I've also talked about the dimension of a vector space and how, if we had, say, 3 vectors in a space that was 2-dimensional, we automatically know that they're linearly dependent. I haven't yet defined what the dimension of a space is, and this is something we'll come back to in a future section. But there is a link between linear independence and spanning sets. Let's say you have a subspace W, which is spanned by m vectors. If the first vector set, doesn't have to be the first, but let's say if one vector, but call it the first one, we'll renumber if needed. If the first vector is in the span of the remaining vectors, then the subspace W was in fact more simply described as the span of the remaining vectors. And so there are ways for you to remove redundant vectors from a spanning set and to obtain the same span with the smaller set of vectors. As a result, as a theorem, there's only one thing to prove here. This is not an if and only if statement. It's a statement that says that if the hypothesis holds, then the conclusion holds, assuming the givens of the problem. So I claim that it is clear that the span of the remaining vectors v2 to vm is contained in W. It is clear because W is the span of v1 and the remaining vectors. So obviously if I look at linear combinations of v2 all the way up to vm, well, I can create out of this linear combination, let's say a2, v2 all the way up to amvm. So that's something that's in the span of the remaining vectors. I can add 0 times v1 to that without changing the linear combination. And now we see that it's written as a linear combination of the vectors in v1 to vm. So anything which is a linear combination of v2 to vm is in W because it's also a linear combination of v1, v2, all the way up to vm. So one of the inclusions is given. Now, in order to show that W is the full span, what remains to be shown then is that if we have something in W, we can write it as something in the span of V2 to Vm. So, okay, let's assume we have something in W. And in W, as this definition here, it's a linear combination of the m vectors. No problem. Now, by hypothesis, what we've supposed here is that V1 is in the span of V2 to Vm. So we can write V1 as a linear combination of the remaining vectors. What does that tell us about W? Well, let's rewrite W properly, we're taking into account the fact that V1 can be written this way. So we're going to substitute this expression for V1 in the expression for little w. So what do we have? We have little w that's going to be equal to a2v2, a3v3, all the way up to amvm for sure, but also a1 times b2v2 plus b3v3 all the way up to bmvm. So we'll put all of the terms that multiply a v2 together. So there's the a2 that would have been right here, but there's also the a1 b2, so a1 times that bit right here that goes in here. So this is what W can also be written as. And written like this, we see that W is guaranteed in the span of V2 to Vm. We can write W as a linear combination of the vectors V2, V3 all the way up to Vm if, this is the hypothesis here, if the first vector was itself a linear combination of V2 to Vm. So W is included in the span of V2 to Vm. The span of V2 to Vm is included in W, or contained is a word I should be using here, not included, sorry. In that case, A is contained in B, B is contained in A. A and B have to be the same. So W is, in fact, the span. What this is saying is that if you have a linearly dependent set, that spans some vector space, W, you can keep on reducing the spanning set, which is what the linearly dependent set is, until you are left with a spanning set that only contains linearly independent vectors, but that still spans the same subspace W. You can remove redundant vectors to end up with a linearly independent spanning set for your subspace. That's a pretty powerful result. If you're looking for a linearly independent spanning set for the subspace W, which is the span of the vectors 1, 0, 0, 0, 1, 0, and 1, 1, 0, how do you find that? I mean, is it even clear that these vectors are linearly dependent to start with? Well, they are, because the third vector, 1, 1, 0, can be written as a linear combination of the first two vectors. 1, 0, 0 plus 0, 1, 0 gives you the third vector, 1, 1, 0. Right, so these three vectors are linearly dependent. They span a subspace, whether they're dependent or not, they still span a subspace, right? The span of any vectors is a subspace. It just so happens to be the subspace that is spanned only by the first two vectors in this case. The third one is superfluous, it's redundant. How do we show that? Well, that third vector we found was a linear combination of the first two vectors. We were lucky in a sense because it was easy to see. Sometimes it's not going to be easy to see and you have to do some mathematical manipulations, which typically involve either solving a linear system or reducing a matrix, which is something we'll explain shortly. But at any rate, here we found that one of the vectors was in the span of the other two. Now, 1, 0, 0 and 0, 1, 0 are also in the span of 1, 0, 0 and 0, 1, 0, right? You can write 1, 0, 0 as a linear combination of the remaining two vectors. If you just have, like, 1 times this plus 0 times this one, and vice versa for 0, 1, 0. So 1, 0, 0 and 0, 1, 0, the span of the two vectors. And then from the big theorem on spans, that tells us that W, the subspace spanned by the three vectors, has to be contained in the span of these two vectors, because every one of these three vectors here is inside this space. So W is contained in the span of these things. But we use the same big theorem here, and basically what this tells us is that 1, 0, 0 as a spanning set, a set that contains only two vectors, it is contained in the other spanning set. And so the span of these two vectors has to be contained in the span of these three vectors. Remember, the span is the set of all linear combinations, right? To combine both of these inclusions, W is, in fact, also the span of the vectors 1, 0, 0 and 0, 1, 0. So here we had originally W being written as the span of three vectors which were linearly dependent. We managed to remove one of the redundant vectors, so we can write W as the span of these two vectors. And it's not difficult to see that these two vectors are linearly independent. Right? When you only have two vectors, linear independence is easy to prove. Is one of them scalar multiple of the other? No. 1, 0, 0, and 0, 1, 0 are not multiples of one another. Formally, see, if I had a dependence equation for these two vectors, if a times the first one plus b times the second one gives me the 0 vector, can I show that the only possible solution is that a and b is equal to 0? Well, yes, I can, because a times 1, 0, 0, that's the vector a, 0, 0. B times 0, 1, 0, that's the vector 0, b, 0. And you end up here with this vector. The vector a, b, 0 has to be equal to the 0 vector. That's the system we want to solve. And the only solution is that a and b is equal to 0. So we managed to write W as a span of two linearly independent vectors. It's good. Now, make note of something. W is in fact a plane in R3. It's the plane that is spanned by the x-axis and the y-axis. It is impossible to take linear combinations of these 3 points and end up with something that has a z coordinate, because all of the z coordinates are zeros. If I take linear combinations, I cannot leave the xy plane. XY plane geometrically is a two-dimensional object. And look at us here. We managed to write this subspace W as the span of two linearly independent vectors. So we've seen that if you have too many vectors in a set, whatever that means exactly remains to be exactly expressed, but if we have too many vectors in a set, the set can't really be linearly independent. Well, how can we enlarge these things? How can we enlarge a set that is a set of linearly independent vectors so that the resulting set is still linearly independent? Right? If we add too many, eventually we'll run out of dimensions to keep all the vectors linearly independent. Haven't yet defined what the dimension is, but that's intuitively the idea. Now, this result here tells us something. Let's say we have a set which is a linearly independent subset of a subspace. So I've picked m vectors in W. All of these things here are vectors in W. And I've picked them in such a way that the m vectors are still linearly independent. That the only way to combine them together using linear combinations and to get the 0 vector is if we were doing the 0 linear combination to start with the trivial one. So let's assume this is the case. Then if I pick any other v in W, you'll have that the set consisting of this new v and the previously m vectors which were linearly independent, this whole set is going to be linearly independent if and only if the new vector that I picked wasn't in the span of the m vectors in W. No, so let's suppose that this is assumed here. Let's suppose that this is indeed the case. You've picked m vectors in a linearly independent subset of W, and now you've picked a v in W. So we have potentially m plus 1 distinct vectors. We definitely have to have m distinct vectors here. This one could, in theory, also be one of the vectors in the v1 to vm, but we don't know. So just call it randomly v. We have two things to show. We have to show that if v and the m vectors form a linearly independent subset, then v cannot be in the span of V1 to Vm. So that's one thing to show. We got to prove this direction, and then we also have to prove the other direction, that if V was not in the span, then in fact the m+1 vectors would be linearly independent. So let's start in the first direction. Let's assume that the m+1 vectors, so the original m vectors that were linearly independent and the new vector that we've added, form a linearly independent set. Then we have a theorem that tells us that no element of this bigger set can be a linear combination of the rest. In particular, V, this thing here, cannot be a linear combination of the other ones. And that's the same thing as saying that V is not in the span of the m vectors. In the other direction, let's say you assume that V is not in the span of the m vectors. So what you need to show now is that the bigger set of m+1 vectors has no non-trivial solution to the dependence equation. A0 times V plus A1 V1 plus all the way up to AM Vm equals 0. Then the only way you can solve that is to have A0, A1, and so on equal to 0. If A0 is not equal to 0, then you could solve for V in terms of the other one, right? If A0 is not equal to 0, you look at the dependence equation here. You send all of the other terms to the other side. And then you divide by A0. So all of this would be possible. And then you'd have that V is a linear combination of the m vectors. But by hypothesis, this is what we've supposed in this direction, we've supposed that V cannot be written this way. V is not a linear combination of V1 to Vm. So that tells us that A0 has to be equal to 0. Otherwise, we have a contradiction. But if A0 is equal to 0, then the dependence equation that you had here basically just reduces to this one. That's a dependence equation for the set V1 to Vm. We know by assumption that this set is linearly independent. And if it is linearly independent, the only solution to the dependence equation is the trivial solution. That means that A1 is 0, A2 is 0, all of the AI is 0. So if you have a linear combination of V and the vectors V1 to Vm that adds up to 0, you don't have a choice. The only solution that it has to be the trivial solution, and hence the set V, V1, V2, all the way up to Vn is linearly independent. Here's an example using polynomials. We're going to look at a set that contains two vectors, x squared and 1 plus 2x. And I'm going to view that as vectors, polynomials, in the space of three-dimensional, or not three-dimensional, of degree 3 polynomials, or degree up to 3. Well, x cubed is not in the span of x squared and 1 plus 2x. I cannot write x cubed as a times x squared plus b times 1 plus 2x. That is not something that can be done, because in order for this to be doable, this linear combination to give me an x cubed, all of the square terms and the constant terms would have to go to 0. And I should have a way to pop up an x cubed in here, and I don't have an x cubed. So clearly x cubed is not a linear combination of these things. What that tells us then is that the set that contains x cubed together with x squared and 1 plus 2x is linearly independent in the space of polynomials of degree 3 or lower. That's from the previous theorem. That's exactly what the theorem says. If something is not in the span of these two things, and these things are linearly independent, we haven't shown that here, but it's not too difficult to show you, something you need to do, then the whole set including this new thing, has to be linearly independent. Another example, you can show that the set of these two matrices is linearly independent. There's only two of them. One vector is not a scalar multiple of the other, so we know that they're linearly independent. This third matrix is not in the span of these two linearly independent matrices, because how would you get one here, right? The corresponding positions, if you do linear combinations, cannot add something which is not equal to 0 here, right? Because the equation would be 0, 0, 1, 0 is equal to a times the first one plus b times the second one. Oh, I should, or b times the first one times a times the second one here. The order doesn't really matter. But anyway, there's no solution in these two parameters here. So this thing is not in the span, so you automatically know that the set that contains these three matrices is linearly independent.